The goal of this project is to explore the use of particle photon, cloud services, and STEMMA QT sensors to develop a system for casting a magic spell. The input will be the motion data of waving the wand. A collection of motion data will then be categorized and recognized as a spell through machine learning. The transformation spell will trigger a P5JS animation. The Leviosa spell triggers a magnetic floating platform. The wand works by using a particle photon with an accelerometer, a proximity and color sensor, powered by a battery pack. The accelerometer detects the coordinates of the movement in order to recognize the shape of the spell. The proximity and color sensors are used to identify which output the wand is directed to, and the color sensor is used to determine the color of the P5JS animation. The final model was a combination of fusion and blender. The base of the wand contains the components, while the body twists to simulate a branch. The tip of the wand has an LED to indicate when the particle cloud is open for listening. The parts were 3D printed and designed to be modular so the wand could be assembled and disassembled for debugging purposes. The result was a fully functional wand with movement, proximity, and color recognition that uploads the data to the cloud in order to trigger the two outputs. Moving on to the machine learning section, we used Edge Impulse to train a machine learning model to recognize 4 different spells using XYZ data from an accelerometer. The training process gathers feature data for each spell and labeling them accordingly. The raw data graph for each spell should be distinguishable from others, yet consistent within its own category. Pick the appropriate processing and learning blocks. Looking at the Feature Explorer, several clusters with clear boundaries were observed. Overall, we got an accuracy of over 90% in VS Code. Set up 2 variables for each spell. Next, create a list called Features for storing raw sensor data to infer a spell. In the setup function, define a particle variable for the transformation, which can be accessed remotely through the cloud using the particle API and p5.js. Call the run classifier function to infer sensor data. When the value for transformation exceeds 0.5, the corresponding transformation spell's Boolean value becomes true, allowing p5.js to fetch it using the particle API. Before moving on to the next part, here is a process map illustrating how the model was trained to achieve its current functionality and accuracy. In the p5.js section, a caterpillar transforms into a butterfly. This transformation is managed in the insect class, which utilizes the start transformation function to trigger the caterpillar into a butterfly. To connect the machine learning model with p5.js, a particle API URL is established for the transformation variable. This allows real-time data fetching regarding the transformation spell from the photon device. During this process, the first input, accelerometer data from the photon device, is read and stored in a list. When the value for transformation exceeds 0.5, the butterfly transformation is triggered using the fetch data function to receive updates from the cloud. In addition to the accelerometer data, the second input, a proximity sensor, recognizes different color bands on the user's hand. For instance, when the user waves the wand, detecting a pink band prompts the caterpillar to transform into a pink butterfly, while a yellow band triggers a transformation into a yellow butterfly. In order to create the floating platform, there were many iterations. The idea that moved forward was to trigger the floating by using electromagnets. Electromagnets are magnets made of coils of wire with electricity passing through them, and unlike regular magnets they can be turned on and off. The first design had a base made out of metal, with 4 electromagnet coils and 8 rows of 3 regular neodymium magnets. We realized that the amount of electromagnets required a great amount of voltage, so the next prototype was simplified. The pinning of the electromagnets in the breadboard proved trickier than expected. At first we used a relay to regulate the voltage. The solution was actually to forego the relay and use instead a transistor and a diode. The successful circuit is as follows. The transistor's emitter connects through the photon's D6 pin and to the negative of the EM coil. The transistor's emitter connects to the positive of the EM coil through a diode, connects to the external battery's positive, and also connects to an LED to indicate if the EM is on. The transistor's base and the external battery are connected to the photon's ground. The final design featured a second platform with a single electromagnet powered by a 4 AA battery pack above the neodymium magnet to pull it upward instead of repelling it. When the coil is turned on, the magnet is attracted and starts floating. In this project, we operated at axolotl levels as it was our first experience with rigging, training, and exploring p5.js. This hands-on approach allowed us to effectively integrate essential technologies. We successfully achieved our expected outcomes by reaching over 90% accuracy in recognizing spell gestures and implementing real-time data fetching with p5.js for dynamic visual transformations. The Magic Spell project demonstrates how AI can transform traditional storytelling and play. The technology enhances the user's sense of agency and immersion, making them feel as though they are truly casting spells.